Welcome to the deep dive. Today, we're tackling something that sounds pretty mathematical, but we promise to make it visual, almost intuitive. We're diving into frequency response, but forget the heavy algebra for a moment. We're going to use geometry. Okay, let's unpack this. Look, if you've ever felt a bit lost in the equations for filters or control systems, you've probably wished for, like, a visual key, a shortcut. Well, that shortcut is the pole zero plot. Our mission today is to show you how placing an X that's a pole or an O is zero on this complex map basically dictates everything. Where the system gets loud, where it goes quiet, even how it handles timing.
Exactly. And the core idea, it's actually quite elegant. It doesn't really matter if you're in discrete time with the Z transform or continuous time with Laplace in the S-plane. The frequency response is fundamentally just the system's transfer function, HEZ or HS, evaluated along a very specific line, a line that represents the frequencies we can actually, hear or measure.
Okay, so what's that line?
For discrete systems, the ones we often use in digital signal processing, we replace Z with e omega. That traces out the unit circle in the Z-plane. That's our frequency racetrack. For continuous systems, we replace S with j omega. That means we're evaluating along the entire imaginary axis in the S-plane.
Ah, okay.
Yeah.
So the unit circle boundary in Z kind of corresponds to the imaginary axis in S.
Precisely. And everything inside the unit circle in the Z-plane maps to the stable left half of the S-plane.
Right, and that clicks instantly. We know stable systems need poles inside the unit circle or in the left half plane. So that boundary, the unit circle or the imaginary axis, that's where the frequency response lives. That's the edge.
That's where the action happens.
So let's set up the math just enough to get to the picture. Any transfer function, h of z, you can factor it, right? You get some constant gain k times a bunch of terms on top based on the zeros, like z.
Right, the roots of the numerator.
Divided by a bunch of terms on the bottom based on the poles, z.
The roots of the denominator.
Yeah.
That factoring is the absolute key.
Because when we plug in z equals z omega.
You get these terms like z omega z. And here's the neat part, that subtraction, geometrically, it's just a vector.
Okay, help us picture that vector subtraction. This feels like the core concept.
Sure. Imagine the Z-plane again. You've got your fixed pole or zero location Z. Let's say it's an O for a zero. Now, e.g. omega is our test point, our frequency point, moving around the unit circle as omega changes.
Right.
The expression e.g. omega z is simply the vector that starts at the zero Z and points directly to our moving point e.g. omega on the circle.
So it's like drawing an arrow from the zero to the frequency we're testing.
Exactly. And the properties of that arrow, that vector, tell us everything.
What properties?
Its length and its angle. The magnitude of that complex term is just the vector's length, the actual physical distance between the zero Z and the point A j omega.
Wow, okay, so forget complex math for a second. It's just distance.
It boils down to distance and angle. That complex equation for a j omega suddenly becomes a ratio of distances and of some difference of angles.
That's much more intuitive. Now, on this unit circle racetrack, where do the frequencies actually sit? Like, where's DC? Where's the highest frequency?
Good question, vital context.
Ugh.
DC, which is frequency to megadollars, is always at the point value 1, the far right side of the circle on the real axis.
Okay.
As you increase the frequency omega, you move counterclockwise around the circle. The highest frequency we can represent in a digital system, the Nyquist frequency, omega pi, sits at z radius 1. The far left side, also on the real axis.
So the whole useful frequency range is just the top half of the circle, from Z1 to Z1.
That's right. Sweeping from megadollars to omega pi traces that upper semicircle.
Perfect. So let's talk magnitude. You said it's related to these distances. How does it work?
It's the gain constant k times the product of all the distances from your frequency point e omega to each zero, divided by the product of all the distances from d omega to each pole.
Product of zero distances on top, product of pole distances on bottom.
Exactly. Which leads to this great analogy. Poles and zeros act like magnets near the racetrack.
How so?
Well, think about the numerator of the zero distances. If your frequency point e.g. omega moves really close to a zero location, that specific distance becomes tiny, right?
Yeah, almost zero.
And since you're multiplying all those zero distances together, even one tiny distance makes the whole numerator, and thus the whole magnitude, plummet. Zeros act like magnets that pull the gain down.
And if a zero is right on the unit circle,
then the distance is literally zero at that frequency. The magnitude goes to zero. You get a perfect null, complete silence at that frequency.
Okay, makes sense. Zeros kill gain. What about poles? They're in the denominator.
Right. So if your frequency point e.g. omega passes close to a pole location, that pole distance in the denominator gets very small.
And dividing by a very small number
Makes the overall result huge.
Yeah.
So poles act like magnets that push the gain up. They create peaks or resonances in the frequency response.
Proximity equals power, basically.
You got it.
So let's sketch a simple filter, a basic low-pass filter. We wanted to pass low frequencies near DC, Z1, and block high frequencies near Nyquist, Z1. How do we place the magnets?
Okay, for a low pass, you want high gain near Z1. So you'd place a pole, maybe slightly inside the unit circle, but very close to Z1. That pushes the gain up around DC.
Makes sense.
And you want low gain near Z1. So you might place a 0 right at Z1 or very close to it. That pulls the gain down for high frequencies.
And a high pass is just the opposite. Pole near Z1, 0 near Z1.
Exactly. You flip the arrangement, poles near neck1 boost the highs, zeros near +1 to cut the lows. Just looking at where the poles and zeros are clustered tells you the basic filter type almost instantly.
That's really powerful. Now, you mentioned resonance. How close does a pole need to be to the unit circle to get a really sharp peak, like in an audio equalizer boosting a narrow band?
Oh, very close. Let's say you have a pair of complex conjugate poles. They always come in pairs if the filter is real. Put them at a radius R at 0.9, maybe at angles 4. You'll get a gentle bump around out of 4,4. Now push those poles out to R and 0.99. That tiny change makes a huge difference. The distance from the circle becomes much smaller when H omega passes by 4. You get a really sharp, high Q resonant peak.
So the radius R directly controls the sharpness, the Q factor.
Absolutely. Closer to the circle means higher Q, narrower peak, more ringy.
Okay, that covers magnitude, the how much. What about the when, the timing, the phase shift? How does geometry handle that?
It handles it just as elegantly. Remember, He omega is a ratio of complex numbers, these vectors.
Right. Each vector has a magnitude, distance, and an angle phase.
And when you multiply complex numbers, you add their angles. When you divide, you subtract their angles.
Okay. I see where this is going.
So the total phase response, the angle of H omega, is simply the sum of all the angles of the zero vectors minus the sum of all the angles of the pole vectors.
Sum of zero angles minus sum of pole angles. Got it.
Each pole in zero contributes its vector's angle to the total phase shift at that frequency.
So if I get close to a pole, not only does the magnitude shoot up, but the phase probably changes rapidly too.
Precisely. As your frequency point H omega sweeps past a nearby pole, the angle of the vector pointing from that pole changes very quickly. That causes a rapid swing in the overall phase response around the resonant frequency.
And that rapid phase change, that's bad for signals, right? It messes things up.
It can, yeah. Especially for things like audio or data transmission.
Yeah.
This brings us to why phase linearity is so important.
What we often want is linear phase response, where the phase shift is just proportional to frequency, like angle H, 2. Why is that the gold standard?
Because it guarantees constant time delay for all frequencies. This relates directly to a concept called group delay.
Group delay, I've heard that term.
Group delay, usually written as 2, is mathematically the negative derivative of the phase response with respect to frequency. So 2 dangle HDO.
The derivative slope. So if the phase is a straight line, like 2, the slope is constant.
Exactly. If phase is linear, its derivative, the group delay, is just a constant, K. A constant group delay means every frequency component experiences the exact same time delay passing through the filter.
Like your marching band analogy. If the group delay is constant, the whole band marches through the gate together. Bassoons and piccolos arrive at the same time.
Perfect analogy. The signal shape is preserved. No dispersion. If the group delay isn't constant, meaning the phase is nonlinear, different frequencies get delayed by different amounts. The band gets jumbled, the signal gets smeared out in time. That's distortion.
And linear phase, you mentioned, often comes from FIR filters with symmetric impulse responses.
That's a common way to achieve it, yes. The symmetry in the time domain, the impulse response, imposes constraints that lead to linear phase in the frequency domain. Types 1, 2, 3, and FIR filters are designed for this.
Okay, so geometry controls magnitude and phase, which controls timing via group delay. Let's look at some special geometries. What about all-pass filters? They have a flat magnitude response, right? Magnitude equal 1 everywhere.
Correct. All-pass filters are fascinating. They don't change the amplitude of any frequency, they only modify the phase. They're like pure time distorters or phase equalizers.
How do you arrange poles and zeros to get flat magnitude? That seems tricky.
The trick is a specific symmetry, conjugate reciprocal pairs. For every pole inside the unit circle at some location t calories, there must be a corresponding zero outside the unit circle at the location $hours.
1 over the complex conjugate. So if a pole is at 0.5, the 0 is at 1.5, and 0, 10.5 equals 2. If a pole is at 0.8, The 0 is at 1.8 EJ TPA4. The 0 is at 1.8 EJJ
I
in pound-cedar OGA.
Exactly. Geometrically, for any point EJ omega on the unit circle, the distance to the pole and the distance to its reciprocal $0 are related in such a way that their ratio perfectly cancels out the effect of the pole's magnitude contribution.
So the distance to the 0 in the numerator perfectly balances the distance to the pole in the denominator.
Precisely, for every frequency. So the magnitude is always K11K. Usually K is said to make it exactly 1.
That's a really neat structural requirement. It shows how the geometry isn't just predictive, it defines the whole class of filter, which leads nicely into system reversibility.
Let's have minimum phase system.
Yes, minimum phase. Very important in practice.
Why do we care about whether a system's inverse is stable and causal? Like, why is reversibility a big deal?
Well, imagine you're trying to undo the effect of a channel in communications, or maybe reverse some processing applied earlier. You need the inverse system to be well-behaved, stable, and causal. Otherwise, trying to invert it leads to signals blowing up or requiring future information you don't have. It creates a real headache for equalization.
Okay, so how does the pole zero plot tell us if a system and its inverse are both stable and causal?
Here's the rule. A stable and causal system has a stable and causal inverse system if and only if all of its poles and all of its zeros are strictly inside the unit circle.
Both poles and zeros have to be inside. Both inside. That's the definition of a minimum phase system. Poles inside guarantee the system itself is stable and causal. Zeros also inside guarantee the inverse system is stable and causal.
What happens if a 0 wanders outside the unit circle? The system is still stable, right? Because stability only depends on poles.
Correct. The original system remains stable, but if you try to compute its inverse, that 0 outside the circle becomes a pole outside the circle for the inverse system.
Yeah.
And poles outside mean instability or non-causality for the inverse.
So for easy reversibility, keep everything poles and zeros tucked safely inside the unit circle. Another clear geometric rule.
It's a fundamental constraint for many designs.
Can we use this geometric thinking for design directly, like, say, designing a notch filter to kill 60 Hz hum?
Absolutely. That's a perfect example. A notch filter needs to create a very deep, very narrow valley at a specific frequency,
So we need gain to be near 0 at that frequency.
which means we need a zero distance to be 0 or very close to it. So what do?
You put a 0 right on the unit circle.
Exactly. You place a pair of complex conjugate zeros directly on the unit circle at the angle corresponding to the frequency you want to eliminate, like 60 Hz mapped to its digital frequency angle.
Since the 0 is on the circle, the distance becomes 0 when E omega hits that exact spot. Magnitude goes to 0. Instant notch.
That's the core idea. It might add some poles nearby, just inside the circle, to control the width of the notch, but the zeros on the circle guarantee the deep null.
It really is powerful. Drawing X's and O's on this map gives you instant feedback on gain and attenuation. We've kind of bypassed a lot of the heavy math.
That's the beauty of the geometric approach. It's a mental shortcut. Poles push gain up, zeros pull it down. Proximity to the unit circle sharpens the features. You can almost sketch a desired frequency response by placing poles and zeros intuitively.
So wrapping this up, what does this all mean for you, the listener? We've seen how pole and zero locations relative to that unit circle path really define the filter's behavior, magnitude, and phase.
The geometry is the frequency response in a way.
And we talked about linear phase being ideal for preserving signal shape because it means constant group delay. But let's flip that for a final thought. What if you have a system with really nonlinear phase, especially where the phase changes rapidly? We know that means group delay is not constant. It varies with frequency.
Right. Different frequencies get delayed differently.
Think about what that does in the time domain. That variation in delay is precisely what smears sharp transients, turns clean pulses into drawn-out messes. It's time distortion caused by nonlinear phase.
But there's a flip side. Sometimes you might not care as much about perfect time alignment. Maybe in image processing, the exact timing isn't critical, just the frequency content.
Okay.
In those cases, designers might choose a minimum phase filter. Remember, that means all poles and zeros are inside the unit circle. These filters often have nonlinear phase, but they achieve a desired magnitude response with the minimum possible overall delay, the minimum complexity or energy storage.
So it's a trade-off. Perfect timing with potentially more delay, linear phase, versus the most efficient way to get the magnitude shape, even if it messes up timing a bit, minimum phase.
Exactly. That choice, often dictated by the pole zero geometry, is a constant consideration for anyone designing filters. What matters more, frequency shape or time integrity? The map holds the answer.